Hello everyone, my name is Thomas Øyvang. I will bring you through this course in power system analysis this semester. This is an introduction lecture to give you an overview of what we're going to look at in this course. The main book for this course is from McGraw-Hill, is by John G. Granger. It is quite a good book for this course, and it has we will go through this chapter 1 to 10 almost for in this book. So we will start at chapter 2 for the basic concepts and go through then chapter 3 and 4 and 5, covering then transformers, machines, transmission lines. Then we go over to chapter 6 and 7, where we look at then, of course, the network calculation and power plant studies. Then we will also go further into different types of faults in the grid, symmetrical and unsymmetrical faults. And then in the end of the course, we also will have a high voltage DC lecture. So then you need one chapter from this book, the direct and current transmission from WD. We will hand this out to you in Canvas, so you can just get it there. Another section will also be on voltage stability. However, it will be on steady state voltage stability and focus on voltage control. So, but this book is also very good regarding this topic, transmission system aspects. Is one chapter here that we will include in the course. In the history of electricity, there are no single defining moment that actually exists. We can say the way we produce, distribute, and install and use the electricity and devices it powers is the culmination of nearly 300 years of research and development. We will use some time just to look at some kind of history and development of electricity. And as you can start from here, in the 1800s, Alessandro Volta built the Voltaic pile and discovered the first practical method for generating electricity. This invention is regarded as the first battery, which can provide a reliable and steady electric current for many researchers to explore more electromagnetic phenomena. The unit of voltage, volt, as we know, is named for Volta's contribution. Further, we can look at in 1820, we have this guy Hans Christian Ørsted from Denmark, not far from Norway, observed that the compass needle moved when the electric current flows nearby for heating a wire. At the same year, the André-Marie Ampere that immediately showed that the force between two long straight parallel wires with currents was inversely proportional to the distance between them and was proportional to the intensity of the current flowing in each. The current unit, ampere, as we know it, or amp, is named after him. Let's go further to the 1827. George Simon Ohm of Germany published the fundamental relationship between the voltage, current, and resistance using the results of his electrochemical experiments, which is now known as Ohm's law, as you probably already know. In 1831, another guy, Michael Faraday of England, discovered the electromagnetic induction through performing a series of experiments. The results of his experiments came with devices leading to the modern electric motor, generator, and transformer. In 1833, Faraday then showed that the electricity induced from a magnet, voltaic electricity generated by a battery, and static electricity were all the same. About the same time, the American scientist Joseph Henry independently discovered electromagnetic self-induction and is also credited with the invention of the electric motor. Yeah, another thing is that the standard unit of inductance, as we know, is Henry, and it's named after him. Inspired by Faraday in 1864, James Clerk Maxwell of Scotland, another famous guy, demonstrated a subtle connection between the electric and magnetic forces, which were now known as Maxwell's equations. Unexpectedly involving the velocity of light. From this connection raised this idea that light was an electromagnetic phenomenon and electricity traveled closely to the speed of light. As this figure gives an overview of the milestone that led to this. With the invention of incandescent lamp by Thomas Edison in 1878 and accompanied central low voltage direct current, the DC, power station built in 1882 at Pearl Street of Manhattan to supply power to 5,000 lamps in 225 houses. The electrification brought a new era of human life. In 1881 to 1884, the Lucien Gollard of France and John Dixon Gibbs of UK demonstrated the advantage of the transformer, which allowed voltage to be changed. About the same time, George Westinghouse had watched with interest in the development of transmitting alternating current, AC, in Europe. So, the development of AC system immediately began in the US in 1885 when Westinghouse acquired the Gollard-Gibbs patents of the US William Stanley, an early associate of Westinghouse, improved and tested transformers in his laboratory in Great Barrington, Massachusetts. There, in the winter of 1885-1886, Stanley installed the first experimental AC distribution system, which supplied 150 lamps in a town. The first AC transmission line in the United States was put into operation in 1890 to carry electric energy generated by hydropower, a distance of 13 miles from Willamette Falls to Portland, Oregon. After the battle between the DC and AC near a decade, the victory of AC system arrived in 1896. When Westinghouse and Nikola Tesla built the first hydropower station in Niagara Falls to send the AC electric power over about 26 miles away to Buffalo, New York. The first transmission lines were single-phase and energy was usually consumed for lighting only. Even the first motors were single-phase, but on May 16, 1888, Nikola Tesla presented a paper describing two-phase induction and synchronous motors. In 1953, the first 345 kV line was built. The first 500 kV line was operating in 1965, and 4 years later, in 1969, the first 765 kV line was placed in operation. Extensive research on high voltage such as 1000 kV has been performed since the 1970s. However, only few of such systems worldwide are in commercialized operation because of the costs. And in Norway we have the highest voltage level from transmission line is 420 kV. The electric power system is regarded as one of the most complicated infrastructure that human beings have been made in the history. Sustainable development of energy resources for the need of residential, commercial, and industrial customers is essential to the continual improvement of standard of living. So it's a great importance to ensure a high quality and reliable electric energy supply while protecting the environment. To achieve this goal, the well-trained engineers are needed to develop and implement the advance of science and resolve the problems faced by the electric power industry. Here we can see a typical grid architecture for the Norwegian power system. And it's mainly three levels that we can look at. Is the transmission network between 420 to 132 kV. Is the regional distribution network, typically from 132 kV to 33 kV. And then you have the local distribution network from 22 kilovolt to 240 volts. And we have both then 400 and 240 volt on the low voltage side, distribution side. Here you can see then the overview coming typically from Norway. We have a hydropower plant, about 96% of Norwegian power production coming from hydropower. We typically have a step-up transformer sending it through the regional transmission network, and then firm to several main transformer station, transformer substation, and of course we're transforming it down to the 22 kV. We have also some 11 kV systems, and down to the low voltage distribution network. Power system operation. So it's mainly three objectives that is important for the operation of the grid, and that is the safety of the system, and people are working on it. And of course it's the reliability, that you can sustain safe delivery of power, and of course losses, the efficiency of the system. So these are three main objectives for the when you operate the grid system. And in Norway we have the TSO Statnett that are doing operation on the transmission system level. In distribution and some regional distribution system, we have companies such as Skagerrak Net, close by here in Porsgrunn. We of course also have markets selling and buying power. We have then the Nord Pool that are currently the market supervisor in Norway. And the classic way, of course, in Norway is the bulk generation, that we produce then, as I said, a lot of hydropower, sending it over a long distance to load centers where we need it. In Norway, we typically power producers are Statkraft and also Skagerrak Kraft or Energi. The TSO in, as I said, Statnett has until now some they call fixed functional requirements in the power system, where they set out a standard how for example, power producers shall operate their generators into the grid. And now there we have also in Europe the ENTSO-E requirement that comes into Norway, where we can have requirements for generators, the RF3, demand connection code, and high voltage direct current connections. All codes are coming into Norway. Bulk generation, as I said, in Norway we have a lot of hydropower, but we can divide it mainly into renewable and variable, such as the solar and wind. We have the renewable non-variable systems, as I said, the hydro, biomass, geothermal, pump storage. And then we can divide it into the non-renewable, non-variable, such as the nuclear, coal, and gas. And all this has to be operated, of course, and also markets. In Norway, we have, to the right here, we have so-called monster mast. That means we have some challenges with the large grid structure. The people want to have it in the ground, but it's of course more costly to do that. But so that's a discussion has been in Norway quite a while, that we should put it in the ground, but the cost is very high.